Okay, take two. I did it before, and yeah, I realized because I was winging it, it wasn't really that nice. So with a little bit more structure now. Let's see. Okay, we left off where we have defined our grid and are able to focus any element within it. And I said we want to use comonads to solve this problem. And just as a quick overview, a comonad is or requires your data type to be a functor and gives you access to 3 functions, and extract is pretty obvious. Whatever whatever we have focused in case for our zipper is the element we will return. Duplicate is kind of hard to verbalize for me. In essence, what it does is it wraps the context around itself. We will see what this means when we implement that for the zipper. And the same holds for extend, but extend just applies a function onto the context, or to the context, I should say. We will just start with the zipper, because we will need the Comonad instance for the zipper anyway. Comonad zipper where okay, do this. Comonad is not in scope. So we have to import Comonad, which means we have to depend on it. Let's restart, then run that. It still works. Now we are missing some implementation details. So we're only required to implement 2 of the functions. We will take extract, and extracting is just whatever we have focused right now. To be returned. It's basically just f, and duplicate is where it gets interesting. We will make this a little bit more obvious. So let's go into the REPL. What duplicate does, in essence, for the zipper is it should return a zipper which has all possible zippers contained within it, focusing each element once. So let's say we make our zipper 3, 4, 5, 6, 7, right? Just our string. We do make zip on z. This x make zip on z is this. So what we now want to have is a list, or is a zipper that contains all possible focused zippers. So in essence, I want right x 2 times right x, and so on and so forth. So what we now can do is we can iterate right on x. This is an infinite list, so let's just limit it. We take, for instance, let's take 7. And now we have a list of all zippers where each element is focused once. And this is what we want to encapsulate into the duplicate instance of the zipper. For that, you will first start with the left side. So we iterate to the left onto Z. And we have to drop the first element, because if we look at iterate, ID, iterate +1, 10, we do this, the first element returned by iterate is the base, or the element we gave it. So yeah, since Z will be the element that is focused, we want to ignore that one. So we also do the same here with right. And since iterate just iterates eternally, or we have to limit this somehow, and for that we will just take the length of the left list as well as the length of the right list respectively, and create our zipper. Zipper LZFCRZ. Nice. So we can reload. Can create our zipper again. Access zipper Z. And now we can duplicate X. This gives us a zipper of all the zippers with each element focused. So let's say I want to print everything here. This does not work because zip does not implement foldable. Just for completeness and to make it viewable, foldable needs map and what do you need again? Fold map or fold R? Fold map. You get a function and a zipper. Function zipper focused right. And all you do is create so this is everything is a list here, so we can just do or use the fold map instance of a list, apply it, plus F plus R. So let's do this, check this out again. This time we can see each zipper on its own line. Nice. Okay, it's the Comonad instance for zip. Not that special. We now want to proceed to do the same for the grid. But grid also has to be a functor. So let's start with that. And functor needs fmap function grid unified. So mapping a function onto a grid simply applies the function to each element within the nested zippers and wraps it back up into a grid. So let's go. We first ungrid, make it even more obvious. So we first ungrid G, then we fmap the function onto G. So now we have a zipper of zippers containing the result of each F. And this just has to be brought back into a grid. Now we have a grid of these. Okay, now we can implement the Comonad instance for grid. Extracting again is pretty straightforward. We first ungrid, so we have a zip of zippers. We then enter or extract the focused element in the first zipper, and then extract the focused element in the inner zipper. Now duplicate. This is a little bit more complicated, so stay with me. Okay, take 3. It's so hard to explain. I don't know why, but I'm still trying to find the correct words. Anyway, so we will start with duplicating the grid. And for that, we will first destructure our grid, just so we can access the sublists. And we want to access the sublists because this allows us to limit the iterations just the same way we had to do take length of L or R respectively. We will first take a look what we want to return. So we want to return a grid that contains a zipper containing something, right? And let's start with the one we focus. So FC. FC is supposed to be a zipper which contains grids. It might be intuitive to say, okay, I have this grid currently focused. And since the outer zipper decides which row is focused, all I have to do is create all grids shifting their focus to the left or to the right respectively. So what we want for the focused zipper or for the focused grid of the wrapped context, all we want to do focused is we want to create a zipper which has the current grid focused, and to the left of it contains all grids shifted to the left. So we drop 1 again, iterate to the left of the current grid. And to the right we do the same. We drop 1, we iterate to the right. And we iterate to the right. So we have to limit the length again. So we take the length of L here. And we take the length of right here. Yeah, okay, we will remove this. So this is our focused. This is our focused zipper, or our focused grid, I should say. A grid, zipper. So this is our focused zipper. A zipper containing all the grids shifted to the left or the right respectively. Since we have to do the same for all rows above and below our currently focused row, we will create a helper function, call it all grids, current grid, which does exactly this. Only for the grid that is given to it. So here it's all grids. And then we make it the same for all up. But this time we have to move the grid up. So for all rows above the currently focused row, we want to apply all grids onto G prime. So yeah, so okay, this would be an infinite list. Again, we have to take the length of the upper list and drop the first element because G is already encapsulated in all focus. And this is all we have to do. For all down, we do the same. But instead of going up, we go down and we limit by all elements that are below us. This is all up, this is all down. And this is the Comonad instance for grid. We will start by first creating a data type for direction. North, northeast, east, southeast, southwest, and west and northwest. And derive show equal for that. Oh, and enum. So we can get all the directions now. We can get all the directions, a list of all the directions. First, I try to just show the solution to motivate why we have to implement certain functions. But no matter how, it always is kinda unintuitive, in my opinion. What I'm gonna do now is just build up primitives for the grid, which we will use to gather substrings into any direction from a focus position. Essentially, if we are here, if we have this X focused, we want to be able to go into each direction and gather a substring. So we want to gather this Xmas here, and we want to gather this Xmas right here, and we want to abort when we go into the top left. So when we go northwest, we want to see, okay, XS, this cannot be right, so we somehow abort into this direction, and this holds true for all directions. For that, what we have to do is be able to shift into any direction. So we get a direction, we get a grid, and we get a maybe grid. And the reason we get a maybe grid is it might be that we are at the first row, for example, and we try to go further north, which does not work because there's no row that is there's no row available to go to. In that case, we would like to return nothing, and we just need some kind of abort. We just need some kind of abort that we can use. And yeah, there's probably a way to do that better or shorter, but yeah, we will just start. Every direction that we use has a set of conditions. So if we go north, we require that we have rows available. Let's unpack our grid. So yeah, if we go north, we want to unpack. If we go north, we want to check, okay, is there a row available? And it is if LZ is not empty. So not LZ. If we go south, it's not allowed for RZ to be empty. If we go east, it's not allowed for R to be empty, and so on and so forth. For west, it's not allowed to have L empty. And for all combinations, like northeast, we can just do condition north plus condition east. Northwest is condition north, condition west. Southeast, condition south, condition east, and then we have southwest, condition south, condition west. And then we also have to do an action for any direction. So if we go north, we want to go up. If we go south, we go down. If we go east, we go right. If we go west, we go left. And for northeast, upright. For northwest, up left. For southeast, down right. For southwest, down left. And now we can just combine all of that jazz into an if statement. So if everything holds true for the given direction we want to go to, we can apply our grid to all actions in that direction. Otherwise, we do nothing. Nice. Which means, if we reload and go ahead and check this, oh, I don't have the grid, right? Let's do this. XYZ, reload. XYZ is our grid. If we shift to the north now in XYZ, we get nothing. If we shift down, so to the south, this works. If we shift to the southwest, this should not work. It does not. Okay. So this does what it's supposed to do. Okay, shifting is done. Now for, let's call it beaming. If we are here, Xmas, I want to get this Xmas, so I want to be able to beam into a direction. So I get a direction, I get some kind of predicate, which allows me to abort beaming or continue. And I get a grid, and I return some accumulated result. And for this case, I know that we will use it with strings, so beam while can also, or will just require the contained element in grid to be able to be compared and be a monoid, so we can just append them. So we have any direction, we have our predicate P and we have the grid. Beaming will use a nested go function. Fine. And what I want to do is I want to have go using the first element or the first focused grid, and then shift the grid into the given direction. So no matter what, the first element currently focused is always evaluated. So what we have here is our, what is it? What we have here is our accumulated result. So in the beginning, it's just the first element. And if we were not able to shift, we can just return the accumulated result. Otherwise, we were able to shift into the direction we wanted to. And what we can do now is make sure that our predicate holds. If our predicate holds for the appended result, so the current accumulated result plus whatever we have currently focused, if this holds, we know we might have to continue. If this does not hold, the predicate was false and we should abort. So we can again just return the accumulated result. So if it holds, we have a new accumulated result, and again we do an append, extract G prime, and we will check and see if, what am I doing? Not shift head, not shift head, there's G prime prime, we just want to shift into the direction. We just want to shift in a direction, G, and if we were able to shift into the direction, then we continue our recursion. Otherwise, we return the accumulated result because the predicate was true before, right? So we have to make sure that they stay together. It's just as part of maybe, so we import this, and beam while is implemented. Okay, so beam while is implemented, and we can now do what we want to do for one grid. So let's just do that, right? What I want to be able to do is, for instance, I want to X, Y, Z. Let's make it result. I want to beam while into, let's go east, okay? Let's go east for a predicate on the grid we currently have. And instead of Xmas, let's use the triple M, so we can see that this works. The predicate we will use is receives a string and returns a bool. And what we will do is simply check if the string is a prefix of target we are interested in, and if the length is compatible, so we only have true substrings. We have to implement this prefix of receives two strings and returns a bool. And for this, all we have to do is get the prefix, the string. We take the length of our prefix we are trying to search from the string and check if it's the prefix. Prefix. That's that, right? So what we can do now is print the result. Print the result. We do a cabal run. And we get MMM. And if we go ahead and make an X out of that one, this should not work. We just get an M. We make an X here, we get an MM. If we have 4 M's, we only get 3 M's. Just like we wanted. Okay. This is everything we already need to solve the problem. But of course now we would like to do this, like beaming, for every possible grid which has, or for any location within the grid that is in focus. And this is now where duplicate will come in handy, because all we can do now is we can duplicate G, which gives us exactly that, all grids that are possible where each location is in focus. And we can apply a function onto every location. So current grid fmap, and oh wait, let's do this. So this is a function that receives a grid focused on any element and shall return any other element. Okay, shall return B, whatever that is. We want to use beam while, and beam while returns in that case a string, so we will get a string. So we have the current grid, and we do a beam while east, beam while east for our predicate and the current grid. And since we want to check every possible direction, not only east, we'll get this and we will create a list. So now we get all the grids. Now we get all the grids here. Rename this. And what we have now is we will get a grid which contains a list of strings. So in essence, we can change this to Xmas again, and we can run our result. This looks a little bit horrific, but we can see that we have Xmas fields and some prefix matches, also some matches which just don't make any sense because the first element is always part of it. We can filter this. So we only are interested in lists that contain our target. So this should be, yeah, this should be better now. Okay, yeah, now we can see that we have 16 Xmas occurrences for each direction. What we can do now is just take the length of each list and then we can call sum. So we sum all the values within the grid. So before this result is a grid of ints, and we can just sum a grid of ints. For that we will need a foldable instance, if I remember correctly. Yep. Let's do that here. Instance foldable grid, and we will just implement fold R. Since a grid is essentially just a glorified list, we can use the fold R instance of a list, but we manually unroll everything. G and unrolled is simply reverse FC FFRZ, and we also have to do the same because unrolled now is a list of zips, but we want a list of lists, so we map that and do the same right here. Now we have a list of lists and we want to join this. For that we need to Comonad join. Now we have a list and we can sum our result. This is 18. Is 18 correct? I have to take a look at oh yeah, it's 18. Okay. Yep. So it's 18. Good to know. Okay, yeah, what we did here is exactly what extract does. So no, not extract, extend. So extend lifts a computation into, or applies a function to the context. And instead of doing that part here, we can just create f, which is going to be this function here. And instead of this, we can just do extend f to g. G. So this is a grid of string. We filter, we take the length. Take the length here. Now we have a grid of ints. Now we can sum that. This should be the same result. And it's 18. Okay. And that's, in my opinion, a super nice. Oh, this looks nice. This is just beautiful. Yeah. We can now go a step further, and instead of beaming, because right now it's kind of rigid, right? So we only can draw straight paths. But what if, for whatever reason, I would like to go in a zigzag line, so S, M, M, X, and I want to get all the occurrences for that. All we have to do now is, we can generalize beam while. instead of working for a single direction, we will create a function, call it traverse, and it looks almost like beam while, but it receives a list of directions instead of a single direction. So we have another, we have an additional abort condition that we have to make sure to respect. So we have our predicate, we have our G, but we'll still have a very, very similar structure. So we have this, shift, but this time we have to take the head of directions, G, and the tail of directions. So we will give go the accumulator, the potential next grid, and the potential next direction we want to go to. Or we want to shift to, I should say. And yeah, this is then very similar. So again, oops, not pred, P. We append, we extract, we do that. This time though, shift, or the next part is shifting head directions, G prime. This is okay, Haskell is lazy, right? So even if this is empty, I can create a nested if and only make sure to evaluate that if it's required, which is right here. This prime, shift to the head of direction, otherwise we accumulate, and this is tail. Okay, yeah, this is traverse, and F is the same. Oh no, it's not the same. Let's do H. It's almost the same. So we get the target, and we don't create a list of beam while. Okay, it's a little different. What was it again? We don't create a list of beam while. So okay, we first start, we traverse a given path with our predicate and the current grid. Traverse a given path. The path we will now choose is okay, let's first do the same. So we will replicate what we did with beam while, just with traverse, just so we know that it's correct and identical. Okay, how does this work again? Oh yeah. Okay, so to be able to traverse, all we have to do is CG. This will be identical target. We will traverse this time where the directions. Yeah, okay, we can just do this. the directions, but the path here is just replicate 3D. HG. This will be identical. Okay, 1880. We only take 3, so because the first focused element always is included, and we only have to add 3 more characters. You continue, which also means that this only works for substrings greater 1, but yeah, I want. So be it. I mean, it's easy to adapt the implementation above. But yeah, what we can do now, FG, let's use J, is change that. We traverse a given path for every location for the current grid. And path, I said I want to do zigzags. So let's do it. We go south. Okay, wait. Before I do that, let's see up here what would be interesting. Yes, okay, let's do this. XMAS, right? So we first go to the left, up, left. Left, up, left. That's the path we're interested in. Couldn't match type with actual type direction. Traverse up and the predicate. And this. Yeah, because traverse is also something in the prelude. Yeah, the CJ, so the result now we can extend J for that stuff, which now returns a grid of strings, which then means, I mean, we can take a look at the result here. It will be a grid of that stuff, and we see that Xmas here that we made out before, and now we want to view it. So let's just traverse that, and traverse returns the string, and we can just check if that string is equal to target. Now we have a grid of bools. What we then can do is from enum, which makes a number out of a bool, which gives us 0, 0, 1s, and then we can also just sum it up, and then we have one occurrence, and that's it basically. So in the end, I mean, lots of stuff to prepare. Having to implement a zipper from scratch might seem kind of overkill, but the fact that this is so adaptable, and I don't know, it just feels nice. It just feels nice. I don't care if it's efficient. It just feels nice to write. It feels nice to think like that, and it's satisfying. Or what else should I say? I love this language, and how it forces one to think differently. I mean, this is something I would have never written, I don't know, 5 years ago or whenever, when I was mainly using iterative programming languages, imperative programming languages. And yeah, nice. I like that. This is good. This is good.